Alright everybody, in this video let's try to implement the remove functionality on a singly linked list. So what exactly this remove operation does on a singly linked list is basically it is used for removing the node at a given position that is requested by the user. To give a specific definition as part of this remove implementation, what exactly we will do is we will basically take the index from the user and we will basically go to this index and whatever the node that we have at that particular index, and we will simply try to remove that node, and in the end we will simply return that node back to the user as a output. Okay, so that is the ultimate functionality of a remove operation on a singly linked list. Here obviously we are taking the index from the user, right? So obviously there would be two cases. The first case is the valid index and the second case is invalid index. Here if you observe the singly linked list that we have, right, we know the valid values of index on a singly linked list will basically start from 0 and will end at length of the singly linked list minus 1. So for the remove operation, the valid range of the indexes will be from 0 till the length of the linked list minus 1. That means in the singly linked list that we have here, right, the indexes will be at 0, 1, 2, 3, 4 and 5. If user passes any of these indexes, we will be able to delete that node and we will be able to return the value. And one thing that you have to make sure here is whatever the head node and tail node and whatever the length that we are maintaining on the singly linked list, right, we have to make sure that those values are still consistent even after deleting the node from the singly linked list. That is something that that we have to remember. Now let's just try to understand whatever the different cases that can come when we are trying to implement the remove operation on a singly linked list. The very first scenario is basically, since we are taking the index from the user, right, first check would be to check if the index that user is passing is invalid. So that is the first check. When we will say the index is invalid, if the index is less than 0 or if the index that is given by the user is greater than or equal to the length of the linked list. If user passes the index that falls into this range, we will simply return null or none based on our programming language that we are using for implementation. If we are using Java or JavaScript, we will simply return null. If we are using Python based implementation, we will return none. Okay, so that is the first scenario. And the second scenario is obviously a valid index that is given by the user. So in the valid index also, what exactly we will do is we will try to reuse some of the functionalities that we have already implemented. So if you remember the previous implementations that we have done it, right, in those cases, basically when we spoke about those functionalities, specifically when we spoke about the pop functionality and the shift functionality, pop functionality is basically used for deleting the very last node we have in the singly linked list, and the shift operation is basically used for deleting the very first node we have on the singly linked list. So whenever the user is passing the valid index, we can reuse this push and pop shift functionalities. So how will we make use of that is, inside the valid index scenario, as part of the first check, what we will do is, if the index that is given by the user is 0, we will check. If it is 0, right, what exactly we need to do? We need to delete the head node, right? We have to delete this head node. That means whatever the next node that we have inside the singly linked list, that should become the new head of the singly linked list. That's why here this operation is nothing but the shift operation. So we will simply call the shift operation with whatever the index or 0 itself we can pass, because whatever the index that user is passing is 0. In the end, this shift function automatically returns the node that it is deleting, right? And we can return that node itself. Okay, so that is the first scenario. And the second scenario is basically if the index that is passed by the user is equal to the very last we have very last index we have on the singly linked list. That is, if the index is equal to the length of the singly linked list minus 1, and we are anyway maintaining the length in our singly linked list, right? And we will be able to get that length directly, and we will be able to compare it very easily as well. So if it is matching this case, that is nothing but we are trying to delete the very last node we have on the singly linked list. That operation is nothing but pop operation. So we will simply call the pop operation directly. Okay, and I forgot to mention, when we perform the shift operation also, we will not pass any index as an argument, right? Because shift operation itself will basically delete the very first node. So it automatically knows that it has to delete the current head node which is at index 0. So this is a small change. By mistakenly I have written index as a function argument. Okay, now the third scenario in the valid case is basically if the user passes any index from 1 till the last but 1th index. In that case, what we have to do is we have to make sure that we are deleting the node at the index that is given by the user. And now I will explain you what exactly is the algorithm that we follow. Now here, let's assume that the singly linked list that we are using for performing the remove operation contains, let's say, some 5 values or 5 nodes in it. And we have the head node and we have the tail node, and these will have some values like 1, 2, 3, 4, 5 or some other random values they will contain, right? And the indexes will be 0, 1, 2, 3, 4. Now we have already understood when the user passes the index 0 and when the user passes index 4, we have already handled those scenarios. Now our worry is if the user passes an index from 1 to 3, right? Now let's assume that in our implementation the index that is given by the user is 2. So we have to delete this node with the value 3 because it is at index 2. Now to delete this node, what we have to do, we have to make sure that whatever the next pointers that we are keeping track of in each and every node, we have to make sure that we are deleting that. So to do that, what exactly we will do is, first we will get the node that is at whatever the index that is given by the user minus 1th position. So in our case, the index that user has given is 2. So we will go ahead and get the node at the index 1th position because we are trying to get the node at index minus 1th position. Because index minus 1th node will contain the next or the reference of the node that is at the indexed position in the next variable of that particular node, right? So we have to make sure that that node we are updating it to the next of the node that is at indexed position. So what exactly we will do, we will get the node that is at index minus 1th position and we will update the next of that particular node with the next of the node available at indexed position. That means that this node's next will be having the value of or the reference of the node 4. In that way, this node is actually getting deleted. Okay, I hope you understood. What exactly we will do is, first we will go ahead and we will try to get the node that is at index minus 1th position, because in that node we have the reference of the node that is at indexed position. So what we will do, we will simply update that next variable or that next value with the next of the node that is at indexed position. So that is the third scenario where index is greater than 0 and less than length of the singly linked list minus 1. That means that the very last index that we have. Let's try to implement the Java implementation of remove functionality. So the function declaration would be public. The return type will be node. I want to return the node that I am deleting at the index that user has passed. And I will want to take the index from the user. I basically want to delete the node that is available at this index. So as part of the basic checks that we do, whatever the index that user has passed might be a invalid index. So in that case, what we will do is we will simply compare if index is less than 0, because the valid index range is from 0 till length of linked list minus 1. We have the nodes in that range only. Or if the index that user has passed, if it is greater than or equal to the length of the linked list, that is this dot length. In this case, there are no nodes at the index that user has passed. In that case, we will simply return null. Okay. If this is not the case, whatever the index that user has passed is 0, that means the very first node in the index we are trying to remove, right? That is nothing but shift operation. So if the index is equal to 0, we will simply return this dot shift. Okay, what shift operation does, it will basically remove the very first node, that is node at the index 0. So we will simply return the same thing. We are reusing the same functionality here. If this is not the case, the other scenario could be whatever the index that I am passing could be the very last index in the singly linked list. In that case, we are trying to remove the last node, that is nothing but the pop operation that we have already implemented. So if the index is equal to the length of the linked list minus 1, that is the last index, in that case we will simply return this dot pop. Okay, so we have successfully handled the case where index is invalid, or if the index is 0, or if the index is the last index, that is length of the linked list minus 1. If none of these condition match, that means we want to delete the node anywhere after the head node and before the tail node. So for that, what we have to do, first let's say that if I want to delete the node at the 5th index, that means I have to go to the node at the index 4 and I have to get that node, so that the next I can adjust to the node that is at the 6th position, right? So first our job is to get the node that is available at the index minus 1th position. So how will I do? I will simply take node, I will define the variable as node, I will simply reuse the get functionality based on the index minus 1. Okay, so I have the index minus 1th node. Now the next will be the node that I actually need to delete will be node to be deleted will be the next of this node, because this node is at index minus 1th position. If I read the next of it, that will be the node at index position. So node dot next. Okay, whatever the nodes that are next to this node to be deleted, that also we want, so that we can adjust it as a next of the node at index minus 1th position. So let me just, what I will do is I'll simply assign node dot next to node to be deleted dot next. Okay, from the node at index minus 1th positions, we have adjusted the next of that to the node that is available at index plus 1th position. That's how we are deleting the node to be deleted. Here you can do simply node to be deleted dot next. We can simply make it null. Even if you don't make it, it's not a issue. You can eliminate this operation as well. After this, basically we basically deleted one node from the single linked list. That means we have to reduce the length by 1. This dot length equal to this dot length minus 1. Okay, now the node that we have deleted is basically node to be deleted that we have written. Okay, this is the basic implementation of remove operation based on the index that user has passed. In all the scenarios, we have reused the functionality that we have already implemented, and in last case we use the get functionality and we have adjusted the next pointers such that we have the consistency across the remaining linked list. Okay, now let's just try to call it and validate the results. Let's assume that the linked list that we have here has 4 values, and let's assume that I want to delete the node at first. Let's try to modify this function to remove. It will take only index. So let me just remove the argument that we have as part of insert operation. Now first we are calling the traverse operation, right, which will basically print all the values, that is 10 coding pile.r true and 10.0. Okay, after that we need to remove the node at index 0, that is 10 itself. That means the new head will be coding pal.r true and the tail will be 10.0. If I execute this, run as Java application, you will see it in the console.log. So before removing, the resulting list is this. After removing, the resulting list is this. In that resulting list, since we are trying to print the head and tail values, you will be able to identify head is this, tail is 10.0, and the total number of nodes are 3, as you can see and count here. Okay, so in the when we passed index 0, it basically went into the logic of shift. Similarly, let's try to pass the index that is same as length of the linked list minus 1. So here it will be 3. If I pass 3, it should basically delete the value 10.0 and the tail node should be modified to true because the logic is going on to the pop operation. So if I execute it, run as Java application, you will be able to validate the same thing here. Okay, if I pass any value that is greater than or equal to length of the linked list, basically we should not perform any operation. So input list and output list should be same before delete and after delete. If I just execute it, you will be able to see the same thing here. Okay, this is how basically we perform the remove operation, based on the index that is passed by the user. Now that we have implemented the remove functionality on a singly linked list, let's go ahead and let's try to understand the time complexity and space complexity involved in this specific operation. So just like any other operation, likewise how we have discussed, let's just try to understand it in terms of both best case scenario and in the worst case scenario. So here, when will the best case scenario of the remove operation will actually occur? Whenever we are trying to remove the very first node on the singly linked list. That means we have certain number of nodes available on our singly linked list and we are trying to perform the remove operation of a head node. That means that we are reusing the shift functionality, right? When the user passes the index 0, we are deleting the head node itself. Obviously, we know shift function will automatically take constant amount of time. So in the best case scenario, the time complexity of remove operation is order of 1, which will basically occur when we are trying to delete the head node of a singly linked list. Okay, when will the worst scenario of the time complexity will actually occur? Whenever we are trying to delete the very last node on a singly linked list. That is nothing but we reused pop operation, right? What exactly pop operation had to do? It has to go to last but 1th node and it has to update the next of last but 1th node to null, right? That's why we have to run a loop for n number of times to reach the last but 1th node. As a result, in the worst case scenario where we are trying to delete the very last node we have on a singly linked list, the time complexity will be order of n, which is nothing but the time complexity of the pop operation. Okay, that is how time complexity and space complexity are calculated in terms of best case and in terms of worst case scenario. Now let's go ahead and let's just try to understand the space complexity of the algorithm that we are writing. Obviously, in the best case, we are reusing the shift operation where we are trying to delete the very first node on a singly linked list. In that case also, we simply, we will not do anything. We will simply take one variable like current head and we will simply update the head node to the next node by using that simple current node or some other temporary variable. As a result, in the best case scenario, the space complexity will be order of 1 only. Okay, so in the worst case scenario, yeah, we will run a loop for n minus 1 number of times to reach the last but 1th node, but we will go to that node with the help of a simple variable called current node. If you remember the pop operation, right, we have taken the help of a current node. Using that current node itself gets updated with the subsequent next nodes as we progress further onto the singly linked list till we reach a point where we are at the node that is at index minus 1th position. As a result, even though we are running the loop for n number of times, we are reusing a simple single variable like current head or some other temporary variable. Okay, as a result, in the worst case scenario also, the space complexity will still remain order of 1 only in terms of performing the remove operation as well. Okay, so that is the time complexity and space complexity analysis of a remove operation on a singly linked list. Okay.